Hi there. For this video, we'll be solving higher order polynomial inequalities. So in the previous videos, we had already tried how to solve linear and quadratic inequalities. So a good question to ask next is, how do we solve inequalities of higher order? Particularly, we are pertaining here to polynomials of higher order degrees such as degree 3, 4, 5, and so on. So to solve higher order polynomial inequalities, the key is similar to quadratic. We simply check for the critical points. So if you don't know critical points, you may check out the previous video or skip to somewhere in this video, as I will have a review here on what critical points are. Aside from this, I also need to emphasize that we need to recall our factor methods, especially in higher order polynomials, since this will be essential in making our lives easier in solving these inequalities. So before we can go on to our example, let us first recall or review what critical points are. So for instance, if we have a given x minus 1, the first step to get the critical point is we first equate this to 0. So that will give us x equals 1. And let's plot this one out here. So this one is the x equals 1. And observe that if we test out the values on the left side, in particular, let's try at x equals negative 3. Then plugging x equals negative 3 to this one, we'll have negative 3 minus 1, which is negative 4. So with the output or the outcome is negative. In fact, if you try each of these points as well as those negative numbers that extend out here, the outcome in this region will always be negative. Likewise, if you try to plug in, say 2, then we'll have 2 minus 1, which is 1, and it's a positive value. And in fact, if you try these values out here, as well as the other positive values on the right side, the outcome on this region will always be positive. And so essentially, that is how critical points work. Critical points are like the point wherein the given expression, in this case, the given is x minus 1. This is the point, the critical point is the point wherein it splits the region into either negative values or positive values, since the value out here is 0. So that is how critical points in a sense work. With that out of the way, let us try solving this one. So the two things that we need to keep in mind is the critical point concept as well as the factoring knowledge of higher order polynomials. Okay, to solve this one, similar to how we did in quadratic inequalities, we start by moving every term to one side of the inequality and leave the right side to be 0. So we'll have here x cubed, then we'll have the positive x squared out here, then negative 7x, and negative 5x less than 0. So simplifying this one on the left, so we combine these two, we'll obtain x cubed plus x squared minus 12x less than 0. So now that we have everything set up on the left side of the inequality and on the right side we have a 0, the next thing to do is to factor this one. So the first thing that we can factor is that since every term has a variable x, we can factor out x and we'll be left with x squared plus x minus 12. Then we have here a quadratic expression. By our knowledge on factoring, the right combination for this quadratic trinomial is x plus 4 and x minus 3. Indeed, if we try to multiply this two, we'll obtain this, and if we add this two, we'll obtain 1, which is the coefficient of this middle term. So that's a quick way to check if this is the correct combination. And from here, since we have already factored the given polynomial into its linear factors, indeed these are linear since the degree of these factors are all 1, we can now get the critical point for this one. So to get the critical point, we simply equate this to 0, this to 0, and this to 0. And that will give us x equals 0, or in the middle, x equals negative 4, or x equals 3. There. So let us resize this first. And let us focus on plotting these critical points to our number line. So we'll have here a number line, and we have here 0. Let's write out 3 here, and negative 4 out here. So with critical points, what it does is it divides this number line into 4 separate parts, or 4 regions. This first, this second, this third, and this fourth region. What we do next is we try to plug in some values. Particularly, we'll have test values for this region, for this, this, and this. And that test value will determine if a certain region is valid to our given inequality. So for this first region, a good test value will be negative 5 since it is less than negative 4. So we can take it. So we'll have here at x equals negative 5. Then we'll have here, so focusing on this one, we'll have negative 5 times negative 5 plus 4. Then negative 5 minus 3. There. Then when this is simplified, we'll have here negative 5 times negative 1 times negative 8, or when combined, we'll have negative 40, which is less than 0. So it satisfies the inequality out here. Therefore, we say that this region is valid, or it is true. Next, we'll have this region out here. So a number between negative 4 and 0 can be negative 1. So trying out negative 1, we'll have at x equals negative 1, we'll have negative 1 times negative 1 plus 4 times negative 1 minus 3. And this will give us -1 times 3 times -4. This simplifies to 12. And this is not less than 0, so it does not match our inequality. Therefore, we can conclude that this region out here is false. Next, we'll have this region out here. So a test value that we can use is, we can use 1. So at x equals 1, we'll have 1 times 1 plus 4 times 1 minus 3, and that will give us 1 times 5 times -2, which is -10, and this one is less than 0. So matches the inequality given, so this region out here is true. So we are only left with the last region, and so we can try to plug in a 4. We can try at x equals 4, since 4 is greater than 3. X equals 4, we'll have 4 times 4 plus 4 times 4 minus 3, and this will give us 4 times 8 times 1, or 32, which isn't less than 0. So since it does not match our inequality, we say that this region is false. Now that we are done with every region, we inspect which region out here are true. Clearly, it's just this first region and this third region. Therefore, we can conclude that x is either less than -4 or x is between 0 and 3. In interval notation, we write this as -infinity to 4 union, this should be -4, so -infinity to -4 union 0 to 3. Just take note that in this answer that we got, the inequality is strict, since the inequality in our given out here is strict. So take note of that one. So we'll now move on to the next and final example. So now we have y raised to 4 plus 8y squared minus 9 is greater than or equal to 0. Fortunately for this example, the right side of the inequality is already 0, so every term is already on this left side. So what we need to do next is to factor this one. Observe that we can let x be equal to y squared. By doing that, we can write this one as x squared plus 8x minus 9 is greater than or equal to 0. And this is simply a quadratic equation. So factoring this one, we'll have x plus 9 and x minus 1. Yep, this is the right combination, since multiplying 9 and -1 will result to this, and adding 9 and -1 will result to this one. So that is, again, the quick way to verify if the factoring is correct. Now we go back to our variable y, which is this one out here. So this becomes y squared plus 9 times y squared minus 1. And note that y squared minus 1 out here still factors into y plus 1 and y minus 1. So basically, we apply the difference of two squares idea in that one. How about y squared plus 9? Note that we can't really factor this one in terms of real numbers. In terms of the complex numbers, this can be factored, but we're dealing with real numbers out here. So we just leave this one. And in fact, there isn't really any critical points in y squared plus 9. So why is that? Again, by definition of critical points, this is the point wherein it splits the region into negative values and to positive values. But by observation, y squared plus 9 will always be positive, since this one is a squared value and squaring a number will always give us a positive value. So positive plus positive will always be positive. So we just leave this one and let's just take note that this one is always positive. Next, we focus on this 2. So getting the critical points of y plus 1 and y minus 1, we simply equate these to 0 to obtain y equals negative 1 here and y equals 1 out here. So now let us resize this one. And let us create our number line. So what we do is we plot our critical points. So that will be negative 1 out here and 1 out here. So we'll have 3 regions out here. So for the first region, this is the region wherein these are the values less than negative 1. So we can take, let's take y equals negative 2, since negative 2 is less than negative 1. So plugging that into this one out here, actually we don't need to include this since this is always positive, so take note of that. So we'll only focus on this one out here. So we'll have here negative 2 plus 1 times negative 2 minus 1. That will give us negative 1 times negative 3, and that is simply 3. And 3 is greater than or equal to 0. So it satisfies our inequality out here. Therefore, we say that this region out here is considered to be true. Next, let's focus on this region in the middle. And a test value that we can use is y equals 0, since 0 is between a negative number and a positive number. So at y equals 0, we'll have 0 plus 1 times 0 minus 1. Again, we'll be only focusing on this 2, since we know that y squared plus 9 is always positive. So 0 plus 1 times 0 minus 1 will give us 1 times negative 1, or simply negative. But negative 1 is not greater than or equal to 0. So it does not satisfy our inequality, and we say that this region out here is false. Let's remove this one. Now, lastly, focusing on our last region, we can take the y value of 2, since 2 is greater than 1. Let's fix the 2. There. So at y equals 2, focusing again on this 2, we'll have 2 plus 1 times 2 minus 1, and that is simply 3 times 1, or 3, which is greater than or equal to 0. So it satisfies our inequality, and therefore we say that this region out here is true. Now that we are done inspecting every region, we can now conclude the solution set for this problem. So we observe that the region 1 is true and the region 3 is true. So therefore, we say that y is less than or equal to -1, or y is greater than or equal to 1. Or in interval notation, we can write this one as -∞ to -1 with a square bracket, union 1, so 1 with a square bracket, to +∞. Take note that in here, the inequality is non-strict. It is non-strict since the given for this one is also non-strict. So see, it's greater than or equal to. And so we conclude that this one out here is the final answer. To end this video, here are 2 exercises that you can work on. So in the first one, we've got z cubed is greater than z squared plus 6z. And on the second one, we've got w cubed plus 36 is less than 9w squared plus 4w. So that's it. Feel free to comment down below your answers and solutions to these exercises, and I hope you enjoyed this video out here and you learned a lot from it. By the next video, we'll probably focus now on inequalities in rational or rational algebraic inequalities. So stay in tune, I guess, or yeah. So that's it, and that is all for this video.